Do you love math? If you do love math, I suggest to go to www.mrmathinc.net or YouTube Mr. Ing today. Very easy and compatible to work with.
Alright, so the fundamental theorem of algebra, formal definition, a polynomial of degree n has n complex zeros. Both are real and non-real. Some of these zeros may be repeated. So let me give you some examples. Alright, so I got a couple examples here. This is a polynomial, f of x equals x squared, and I drew that squiggly line because I'm not showing you the rest of it. I just want you to kind of see the parent function. Here's an example where this one is called the repeated. Does that make sense? Here's an example, f of x equals x minus 1 squared. Does that make sense? Because if it's both x minus 1 times x minus 1, you solve that, and you get x equals 1 and 1. Do you see how it's repeated? We've actually talked about that. That's the multiplicity, right? The bouncing off or the kissing. All right, so went over that example. This example here, and all these examples where they cross the x-axis. What did I just say, class? So anything here in yellow, those are going to be our real solutions. Count with me. Ready, set, go. 1, 2. So this one has 2 real solutions. X equals 6, right? X equals -2. Those are real solutions. Here, how many real solutions do we have, class? I know you count at 1, but that's where they count this one as, like, they call it a double root. So you still have 2 real solutions. It's just the number's the same. Okay. Now we learned previously in leading coefficients that the power tells you how many max real x-intercepts. Okay, so it's telling us max 2. Max 2. But look at this one over here. Class, does this one cross the x-axis? No, so what color did I not use? I'm gonna get that on colors. What color do I have that I haven't used? I have a highlighter. Alright. So this distance off the x-axis, that is called a non-real solution, or a complex. Okay, so I have 2 zeros, but they're not crossing, right? So we call this 2 complex solutions. It's going to have an imaginary number. It's going to have I in it. Does that make sense? So, and then this graph here, we have max 3, but if I look at my graph, how many real zeros does it have? 1 real 0, or solution. Okay, that means it has how many complex? 2 complex. Because 1 plus 2 gives me the 3 that I need. Remember, that's the max. That's the max. Okay. So the fundamental theorem of algebra basically says if it crosses the x-axis, it's going to be a real solution. And if it doesn't cross the x-axis, you're going to have things called non-real or complex solutions. All right, let's further talk about the fundamental theorem of algebra. I gave you guys that example on the previous slide that had a quadratic that did not touch the x-axis. Class, what's the degree of this graph?
2.
The degree is 2. And how many reals does it have? It has 0 reals because it doesn't touch the x-axis. Therefore, how many imaginaries do you have? You have 2. What this implies is that imaginary roots come in pairs. So from this example, I'm proving to you that imaginary roots come in pairs. Because we said it doesn't touch the x-axis, but my degree is 2, so I'm trying to figure out where are the other zeros. It must be imaginary. So in this example, it says, well, before we get to the examples, let's draw a picture. Pairs is how many? Let's draw 2 stick figures, you and your best friend. If one of you is called A plus BI, then the other person must be called A minus BI. Do you guys remember this? It's the conjugate. Let's circle that. Conjugate. Okay? Tin can's gonna fall. Perfect. Push this up anymore. Alright, so let's do this example now. If 3 minus 2i and 5i are roots of a polynomial equation, what are the other roots? So, let's review back here. The first part is the real, and the second part is the imaginary. So I have 3 minus 2i. Class, what's its conjugate? This would be a plus. So it's, where are the other roots? What's its pair? 3 plus 2i. Let's write this one. Now this one only has 5i. They call this a pure imaginary. What's its real then? There's no number here. 0. And question, is 5i positive or negative? Positive. So what would its conjugate be? Its conjugate pair? Negative 5i. And you don't need to write the 0, do you? But if you do need to, it can help you understand. So what are the other roots? The other roots are 3 plus 2i and negative 5i. Hey guys, let's go over this example of the fundamental theorem of algebra. And we have the polynomial function 6x to the third minus 23x squared plus 12x plus 20. Notice it's in descending order, so the highest exponent is in front. That would be to the 3. So this is a third degree polynomial. And our degree is equal to the real plus imaginary zeros. Degree is equal to the real plus the imaginary. So the highest degree. And now we're trying to figure out the type of zeros. Are they real or imaginary? Imaginary or complex has the letter I, and the real. And what we've done here is use the synthetic division or synthetic substitution to figure out one of the zeros. We found that using x equals 2. We found the remainder is 0, the remainder of the theorem. It helps me factor 1, and then I can factor the other one. And these are my zeros here. X minus 2 is our factor, so x equals 2, x equals 5 halves, and x equals negative 2/3. Are there any i's in there? No. Remember, we talked about how there's no imaginary there, no imaginary there, no imaginary there. So we have 0 imaginaries in this problem, and we have 3 reals. So in this case, we solved for the zeros. Let's apply the fundamental theorem of algebra. Look at our original problem. Point to it. Put your pencil or finger on the highest degree. Circle it. The highest degree is what, class? 3. So n equals 3. Now I wrote down this formula. You can write that on your notes if you want. Well, if our degree is 3, It has to equal the real number of reals plus the number of imaginaries. Well, how do I know if they are real or imaginaries? We haven't graphed it. Well, we actually solved for the binomials here, and you can just apply the zero product rule, and we can solve for our x-intercepts here. So I can do x minus 2 equals 0, x plus 3 equals 0, and x minus 2 equals 0. And if you solve for x, x is equal to what? Negative 2, negative 3. So who said 2, negative 3, and 2? Okay, so count with me. Ready, set, go. 1, 2, 3. Do you have any imaginaries or eyes in there? Do we have any? No. So in this problem we have 3 reals and 0 imaginaries. How do you know if you get an imaginary? Well, you'll have to have I in there, right? The square root of negative 1.
Yo. 2 plus 2 is 4, minus 1, that's 3 quick maths. Everyday man's in the class, doing problems. See that problem board, that problem is easy. Thanks to Mr. Ng.